In this project, I was responsible for predicting daily bike rentals using a linear regression model. I used Google Colab to complete my analysis and predict how many bikes are rented every day over the span of 2 years. First, I loaded in the necessary libraries for all the code I wanted to run. If I didn't load all these libraries in, I would not be able to make the graphs I needed or generate a linear regression model. Then I loaded the CSV file that had all the bike rental data, and I saved the data in a data frame called df_bike. Next, I calculated the dimensions and found that the data had 731 records, or rows, and 14 columns. I did this by using the shape feature in Google Colab. I also listed the columns in the dataset along with their types, using the dtypes function in Google Colab. Then I previewed the data with the head function. In the year column, 0 represents 2011 and 1 represents 2012. The months are ordered from 1 to 12 and the weekdays are ordered from 0 to 6. 0 represents Sunday and 6 represents Saturday. The seasons are also represented with numbers. For the holiday column, 0 means that the day was not a holiday, and 1 means that it was. The same applies for working days. 1 represents Monday through Friday, aka working days, and 0 represents Saturday and Sunday. The weather indicators are temperature, atemp, hum, and wind speed, and those numbers are normalized. 0 represents the lowest value, and 1 represents the highest value. The last 2 columns are regarding the rentals. Casual rentals refer to people that rent the day of their ride and don't have an account for whatever reason, and registered rentals refer to people who register with the bike rental system and most likely rent more often. Next, I created a new column called total_rentals, and it was the sum of casual and registered rentals. I previewed the data with the head function and calculated the dimensions again. Notice how there's 15 columns now instead of 14 since we added the total rentals column. I also generated descriptive statistics for the columns in the dataset using the describe function. This allowed me to see the count, mean, standard deviation, minimum, and maximum values for each column, as well as the values for the interquartile range. I also created a pivot table with the year and month as indices that sums and averages total rentals. Then I determined that if there are any missing values in the dataset with the isNull function and found that there were none. Next, I moved on to generating graphs. I generated a histogram to visualize the distribution of data in the total rentals column. I also generated a scatter plot with casual rentals on the x-axis and registered rentals on the y-axis, and I color-coded the dots based on whether it was a working day or not. Based on the scatter plot, it looks like there are more registered rentals on working days and more casual rentals on the weekends. I also generated a swarm plot with season on the x-axis and total rentals on the y-axis. Season 1 seems to have the lowest average daily rentals. I generated a line plot with month on the x-axis and total rentals on the y-axis. And it appears that daily rentals had increased between 2011, which was year 0, and 2012, which was year 1. Finally, I created a pair plot to show the relationship between total rentals and weather indicators. Then I created a new variable called bike_heatmap, so I could create a heat map and show the correlation between total bike rentals and weather indicators. For the last portion of this project, I needed to generate a linear regression model that showed the relationship between independent variables, the weather indicators, and the dependent variable, total bike rentals. I only included independent variables that had a correlation coefficient R with respect to total rentals that is greater than 0.5 and less than negative 0.5. I did not include atemp, since atemp stood for what kind of temperature the day felt like, and thus is highly correlated with the temperature of the actual day and not independent. Because of these parameters, I only had one independent variable, which was temp. I separated the independent variable from the dependent variable, total rentals. Next, I split the data into training and test sets using the train_test_split function. I then fit the linear regression model using the training data and printed the intercept and coefficient. The intercept was 1,327 0.93 rounded, and the coefficient was 6,463.97 rounded. Following these steps, I predicted how many rentals the company would have in one day if the temperature of the day was 0.3 normalized. The model predicted that the company would have around 3,267 rentals on a day where the temperature was 0.3 normalized. Finally, I predicted the total bike rentals in the test data and saved the predictions for every day in a variable called y_predict. And these are all the predictions for every single day based on the model. At the end, I generated the r-squared value, which turned out to be 0.75 rounded. 0.375 rounded. The r-squared value indicates how much variation of a dependent variable is due to the independent variables in a regression model. According to this r-squared value, the variation in total bike rentals is not explained very well by the temperature of any given day, but there is some variation in total bike rentals due to the temperature.